A modern excavator is considered worn out after just 10,000 hours. But in the cable era from 1920 to 1970, machines somehow survived beyond 120,000 hours, 12 times longer, powered only by friction drums, wire rope, and human skill. How did technology from a century ago outlast everything built today? And what design secrets did we abandon? To answer that, we have to start at the very beginning. Long before the cable excavator became an icon of mining and construction, the groundwork was laid in the age of steam and iron. In the 1830s, German engineers invented wire rope, a breakthrough that replaced brittle chains and hemp with flexible steel strands, strong enough to lift unimaginable weights without snapping. By 1836, William Otis introduced the first steam-powered shovel, a hulking machine that used chains to drag its bucket through earth. These early giants helped carve railways and canals, but their chains wore quickly, and their steam engines demanded constant tending. The arrival of wire rope changed everything, and steel cables could run over pulleys and drums, carrying the full force of a loaded bucket while surviving years of daily strain. By the late 19th century, cable systems powered trenching machines, drag lines, and backhoes, each one evolving to handle tougher jobs and heavier loads. Patent records from the 1890s show inventors racing to refine cable routing and drum designs, seeking smoother motion and fewer breakdowns. Emphasis on wire rope transformed heavy work. Then came electrification. The true leap arrived in the 1920s as coal mines and road projects grew ever larger. Manufacturers like Bucyrus, Erie, and Marion Power Shovel began fitting their machines with electric motors, and gone were the days of stoking boilers and wrestling with steam valves. By 1926, the Bucyrus 120B entered production, combining electric drive with robust cable systems. That model proved so successful that over 300 units rolled out by 1951, each capable of moving mountains of earth for decades. This era is defined by electrification and steady power. Throughout the 1930s and 1940s, cable-operated excavators scaled up in both size and power. In open-pit mines, machines weighing over 170 tons became common, their buckets swallowing 5 cubic yards at a time. The rhythm of spinning drums, the hiss of cables under tension, and the steady hum of electric motors defined the soundtrack of industrial America. These machines, built on the foundation of 19th century wire rope and early electrification, set the stage for a new era where durability and mechanical mastery became the gold standard in heavy equipment. Every cable-operated excavator built between 1920 and 1970 was engineered around one principle. Every part had to be repairable, serviceable, and ready for decades of punishment. The heart of these machines lay in their friction drums, massive steel cylinders often grooved with multiple channels, each guiding a separate cable for hoist, crowd, or swing. These grooves were not just for organization. They distributed wear evenly across the cable and drum, letting operators swap out a single cable or drum section without dismantling the entire machine. Drum ratios, carefully calculated by engineers, multiplied the force applied by the operator, making it possible to lift tons of earth with a modest electric or diesel motor. Stopping and controlling all that motion called for robust brakes. Cast iron brake shoes, lined with replaceable friction material, clamped down on spinning drums to hold a load or feather a swing. When a brake wore thin, mechanics could unbolt the shoe and fit a new one in minutes. This modular approach extended to every cable, bearing, and clutch in the machine. Cable kits came in standardized lengths and gauges, often supplied with detailed labels from the manufacturer, Bucyrus, Marion, P and H, so a remote mining crew could order replacements by part number, not guesswork. Oil bath housings protected the main bearings and gears from dust and grit. Instead of relying on sealed hydraulic systems, these excavators used gravity to keep oil flowing over moving parts. Mechanics topped off reservoirs daily, and as long as oil was present, the bearings could run for years without metal-to-metal contact. Operators could inspect, clean, or replace components with basic tools, and every critical part was designed to be reached without removing half the machine. Manufacturers enforced strict labeling conventions, stamping serial numbers and part codes directly onto castings and gearboxes. Service manuals, sometimes hundreds of pages thick, mapped out every component and listed routine checks. This was not just for convenience, it was a survival strategy. In the middle of a coal field or open pit mine, downtime meant lost revenue, and every hour saved in repairs added to the machine's lifespan. The result was a system where nothing was hidden, nothing was disposable, and every repair brought the machine one step closer to its next 10,000 hours. These design choices laid the mechanical foundation for the remarkable longevity that would become the cable excavator's legacy. Running a cable excavator demanded a level of coordination that bordered on the impossible. Operators perched in high, drafty cabs, surrounded by a thicket of levers, pedals, and spinning drums. Each shift began with a ritual, a quick scan of the control panel, hand settling on 6 main controls: hoist, crowd, swing, dump, boom, and propel. Every movement mattered. A single misstep could send a loaded bucket swinging wildly or bring a 70-ton boom crashing down. One retired operator, now in his 80s, recalled his first day on a Bucyrus 120B. He said, "It was like needing an octopus for co-pilot. You needed 6 hands and 3 feet, and you only got 2 of each." He was not exaggerating. The hoist lever controlled the lift of the bucket. The crowd lever extended or retracted the dipper arm. The swing pedal rotated the house. Another pedal dumped the load, while a separate lever or foot bar managed the boom's angle. Even the propel function, moving the entire machine, required its own dedicated control, often engaged with a heavy steel bar. Unlike modern excavators, where joystick controls translate gentle hand movements into smooth hydraulic action, cable machines demanded constant manual input. The operator kept both feet and both hands in motion, feathering brakes with the right foot, modulating the swing with the left, and finessing the hoist and crowd levers with both hands. Each action was interdependent. Letting go of the wrong control could send tons of steel and earth into uncontrolled motion. The rhythm resembled a pianist performing a 6-part fugue, except the keys were iron levers, and the stakes were measured in tons, not notes. Training was relentless. Apprenticeships stretched for months, sometimes up to a year, before a new hire was trusted with a full production shift. In the 1950s, coal companies and construction outfits paid cable shovel operators 2 to 3 times the wage of a laborer. The reasoning was simple. A skilled hand could complete a dig cycle in under 30 seconds, moving hundreds of tons per hour, while avoiding the kind of mistakes that led to catastrophic damage or lost time. Operators learned to read the subtle feedback from the machine, the tension in the cables, the sound of the drums, the feel of the brakes underfoot. Veteran crews could tell by the pitch of a spinning drum or the vibration in a lever whether a cable was about to fray or a bearing needed grease. This sensory awareness was not just a point of pride, it was a survival skill. Inside the cab, the choreography never stopped. One hand would ease the hoist lever, while the other nudged the crowd. A foot feathered the swing pedal, counterbalancing the load as the bucket arced toward the dump point. The operator's eyes darted between the cut, the bucket, and the cables, always anticipating the next move. In the words of one foreman from a 1948 training manual, "You don't operate a cable shovel, you conduct it." This mastery did not just move earth, it extended the life of the machine. Smooth, coordinated operation meant less shock to the cables, fewer snapped drums, and a fraction of the breakdowns seen in rougher hands. The best operators were legends in their own right, known by name across entire mining regions, recruited for the biggest jobs, and remembered decades after their last shift. In the world of cable excavators, human skill was every bit as important as steel and grease, and the memory of that lost expertise lingers wherever one of these old giants still runs. A loaded bucket, swinging on a steel cable, carries more than just earth. It carries the full force of physics. Every movement in a cable excavator is a contest with gravity and momentum. When an operator pulls back the hoist lever, the bucket rises, but the real test begins when it starts to swing. Unlike modern hydraulics, which freeze in place the moment controls are released, cable systems obey the laws of inertia. Let go of a lever too soon, and the bucket keeps moving, sometimes with disastrous results. The entire machine becomes a giant pendulum, amplifying even the smallest mistake. The most feared scenario was a runaway load. If a brake slipped or a foot missed its mark, tons of steel and rock could whip across the pit, smashing into anything in their path. Veteran operators recall startup collisions, moments when a misjudged swing sent the boom crashing into the cab, tearing through sheet metal and glass. In those early years, there was no safety glass, no reinforced operator compartment, just a thin metal shell between man and machine. The margin for error was measured in seconds, and the consequences could be fatal. Pendulum physics ruled every cycle. A full bucket, once set in motion, resisted any attempt to stop it. The operator had to anticipate the swing, feathering the brakes and drums in perfect rhythm, or risk losing control. If the bucket overran the dumping point, could drag the entire machine forward or topple it sideways. In deep pits, a runaway load meant more than lost time. It meant equipment damage, injuries, or worse. Mining accident records from the 1930s and 1940s describe cable shovels that toppled into their own cuts, pulled by the unchecked force of a swinging boom. Gravity was both ally and adversary. It powered the bucket's descent, but it punished any lapse in concentration. Operators learned to read the subtle cues, the tension in the cable, the hum of the drum, the feel of the brake pedal beneath their boot. They developed an instinct for timing, knowing when to ease off and when to clamp down. Even so, mechanical failures lurked in every shift. A frayed cable or worn brake pad could turn a routine cycle into a catastrophe. Regulators took notice. By 1911, the U.S. Bureau of Mines issued bulletins warning of hoist rope accidents and runaway loads, urging operators to inspect cables and maintain brakes. State labor codes started requiring drum guards and regular safety checks by the 1920s. But for decades, the real defense was operator skill. Safety codes evolved slowly, often in the aftermath of high-profile accidents. But no rule could fully tame the momentum hazard built into every cable excavator. The urgency for safer, easier controls grew with every incident. As machines grew larger and more powerful, the risk multiplied. By the 1950s, open-pit mines ran shovels weighing over 170 tons, their buckets swinging with the force of a wrecking ball. Each cycle demanded total focus, and each misstep carried a price. The relentless dance with gravity defined the cable era, an era where physics set the rules, and every operator learned them the hard way. Before a cable excavator's engine ever turned over, the day began with a ritual that could stretch for an hour or more. Mechanics and operators gathered around the machine, grease guns and oil cans in hand, ready to attend to dozens of lubrication points scattered across the frame. On a Bucyrus 120B, the tally reached as high as 54 grease fittings, each one hidden behind a guard, tucked beneath a drum, or perched atop a pivot. Every fitting demanded attention. Miss a single one, and a bearing could seize, a cable sheave could grind itself to dust, or a boom pin could weld itself in place from the heat of friction. Blackjack grease, thick as tar and stubborn in cold weather, was pressed into zerks by hand. Operators pumped until new grease oozed from the joint, purging water and grit from yesterday's work. Oil cups, small brass reservoirs perched above moving parts, were filled and checked for leaks. The scent of oil and metal hung in the morning air, mixing with the dust of the pit. Each fitting, each cup, each drop of lubricant was an act of insurance, a promise that the machine could keep running through another punishing shift. Cables, too, required constant vigilance. Every week, operators inspected for broken wires or flattened strands, running gloved hands along the length of each hoist and crowd cable. If a cable showed more than a few broken wires in a single lay, it was marked for splicing or replacement. Splicing, a skill passed down from one operator to the next, meant cutting out the damaged section, weaving the ends together by hand, and binding them with wire. In the largest mining shovels, a full cable splice could take half a day, and a team of 2 or 3, but it kept the machine out of the scrapyard and in the pit. The maintenance logbook became a second Bible. Each fitting had its own schedule, some needing grease every shift, others every 40 or 50 hours. Oil bath housings for the main drums and gearboxes were checked for level and clarity. If the oil turned milky or dark, it was drained and replaced on the spot. Bearings were pulled and cleaned at set intervals, sometimes every 10,000 hours, sometimes sooner if the operator felt a new vibration or heard a change in pitch from the drums. These were not just guidelines, they were survival tactics. In remote pits, a failed bearing or frozen pin could sideline a machine for weeks, waiting on parts that might be hundreds of miles away. The labor invested was staggering. For a single 120-ton shovel, a full maintenance round could mean 2 men working for hours before and after every shift. In winter, they chipped away at frozen grease and fought to keep oil flowing. In summer, they battled dust and grit that worked its way into every joint. Yet this daily discipline paid off. Machines that received meticulous care outlasted their rougher counterparts by decades. Operators took pride in spotless zerks and smooth-running drums, knowing that every minute spent with a grease gun meant hours saved on the job. Restoration teams today marvel at the evidence left behind. On preserved machines, original grease fittings still bear the marks of thousands of pumps. Some restorers find oil residue deep inside housings, proof that the old rituals worked. In shop manuals, maintenance charts are dog-eared and stained with oil, a testament to the hands-on culture that kept these machines alive. The routine was never glamorous, but it was essential. Every fitting greased, every cable inspected, every bearing cleaned, these small acts, repeated day after day, added up to the legendary longevity of the cable excavator. On the pit floor, the real measure of a machine was its cycle time. Every minute counted in open pit mining, where a single excavator could determine whether a crew finished ahead or behind schedule. In the 1950s, superintendent memos from coal fields in Ohio and Pennsylvania tracked these numbers obsessively. A well-tuned cable shovel, operated by a skilled hand, could complete a full dig, swing, dump, and return in as little as 28 to 32 seconds. Over a 10-hour shift that translated to more than 1,000 cycles, hundreds of tons moved before lunch. Comparisons with early hydraulic excavators began to surface in the late 1960s, as contractors weighed their options for new equipment. Internal reports from mining companies documented side-by-side tests. In one such trial, a Bucyrus 120B cable shovel averaged 31 seconds per cycle in loose overburden, while a first-generation hydraulic machine clocked in at 34 to 36 seconds per cycle, under similar conditions. The difference was not just academic. Over a week, the cable machine moved thousands of extra tons, shaving days off a stripping job. Operators noticed, too. Forum recollections from the era recall a sense of shock when hydraulics failed to outpace the old cable giants, at least in the hands of experienced crews. But speed on paper was only part of the equation. The real debate played out in boardrooms and procurement offices, where economics often trumped raw performance. By the late 1960s, the price of training a cable shovel operator had become a sticking point. Apprenticeships could stretch for 6 months or more, with wages running 2 to 3 times that of a standard laborer. A Midwest mining superintendent in 1968 spelled out the dilemma. The memo said that cable shovels delivered faster cycles and lower downtime, but operator cost now exceeded machine cost over 5 years. Hydraulics allowed training a new man in 2 weeks. The economics grew starker as hydraulic technology matured. Modern hydraulic excavators required overhauls at intervals of 7,000 to 10,000 hours, roughly every 3 to 5 years in heavy use. Parts and labor for a major hydraulic rebuild could run into 6 figures, especially as machines grew more complex. By contrast, cable shovels routinely ran for decades, with modular repairs such as new cables, brake linings, or bearings completed on site for a fraction of the cost. Yet as the labor market tightened and infrastructure projects multiplied, the ability to hire and train operators quickly became a decisive factor. Even as cable machines proved their mettle in cycle tests and long-term costs, the industry shifted toward equipment that anyone could run, with minimal instruction. Procurement records from the period show a clear trend. By 1970, hydraulic orders outpaced cables by nearly 3 to 1 in construction and general contracting. Mining held out longer, but the writing was on the wall. The speed advantage of cable excavators was real, but it was no longer enough to justify the higher training investment. The cycle tests had settled the technical debate, and economic logic decided the winner. In the end, the fate of the cable excavator was not sealed by a stopwatch, but by a spreadsheet. The machines that once set the standard for productivity and endurance found themselves sidelined, not because they were slow or weak, but because the world around them changed. As the last superintendent memos noted, the old shovels still outdig the new ones, if you can find a man to run them. At the far end of the cable era, the scale of excavation machines reached almost mythic proportions. In 1969, the Bucyrus Erie 4250W, better known as Big Muskie, stood as the largest walking drag line ever built. Weighing in at 13,500 tons, it towered over the Ohio strip mines like a moving factory. Its bucket alone held 220 cubic yards, enough to swallow a full-size house or 6 highway dump trucks in a single bite. When operators swung that bucket through a cut, the earth gave way in slabs, not shovelfuls, and each pass shifted the landscape by the ton. Big Muskie's statistics defy easy comparison. The machine stretched nearly 500 feet from boom tip to counterweight, with a boom that rose higher than a 20-story building. Its electric motors drew as much power as 27,500 homes, requiring coordinated night shifts to take advantage of lower electricity rates. Over a 22-year career, Big Muskie moved 483 million cubic yards of overburden, carving out coal seams that fueled power plants across the Midwest. At peak, it could shift 8,000 cubic yards an hour, and its calculated operating hours, running 24 hours a day, 364 days a year, approached 190,000 hours, a number that dwarfs the lifespan of any modern hydraulic excavator. But Big Muskie was not an outlier. The 1960s saw several machines in its class, each a testament to industrial ambition. Marion Power Shovel 6360, known simply as the Captain, tipped the scales at over 12,000 tons, and moved 800 million cubic yards before its retirement. Even smaller giants, like the 172-ton Bucyrus 100B, became common sights in open-pit mines through the 1950s, their 5-yard buckets devouring earth in a steady rhythm that defined the workday. The sheer size of these machines dictated their own rules. Crews worked in shifts just to keep them greased and fueled. Maintenance platforms ringed the superstructure, and ladders climbed up to engine rooms the size of cottages. When a cable wore out, replacing it meant hours of rigging and a team of men threading steel rope through pulleys as thick as tree trunks. Every component was oversized, drums measured in feet, not inches, and a single gear could outweigh a family car. For those who worked on or around these machines, the numbers became a kind of legend. Museum curators today point to the surviving buckets and boom tips with a sense of reverence. A 220 cubic yard bucket, painted bright red, sits on display at Miners Memorial Park in Ohio, a silent monument to the era when moving mountains was a daily routine. Visitors climb inside, tracing their hands over steel worn smooth by decades of rock and mud, trying to imagine the force required to fill it again and again. The industrial impact of the cable era is measured not just in hours or tons, but in the physical transformation of the land. Strip mines, highways, and reservoirs across North America bear the scars and signatures of these machines. The legacy of their scale endures in every open pit and every preserved relic, a reminder that, for a brief window in history, human ingenuity and mechanical muscle combined to move the earth itself. In a quiet workshop on the edge of a Midwest industrial park, a small group of volunteers gathers every Saturday, year after year, to breathe life back into machines once thought lost to time. The centerpiece of their effort was a battered Bucyrus 50B. Half buried in mud for decades, its paint flaked away, gears locked with rust, and cables tangled like forgotten vines. The first task was simple in description, but daunting in practice. Remove decades of grime and corrosion without destroying the original castings. Each bolt, each bearing, was cataloged, cleaned, and when possible, restored. When parts were too far gone, the team scoured old mining towns and contacted former operators, searching for spares in barns, fields, and scrapyards. Some components were recast from original patterns, funded by donations from enthusiasts who remembered these machines from childhood visits to strip mines. The restoration lead, a retired engineer named Walt, kept a logbook that reads like a diary of setbacks and small victories. In the first year, the team managed to free the main drums and replace a handful of grease fittings. By year 3, the cab controls moved again, and the first tentative swing of the boom brought cheers from the crew. The project stretched on for 7 years in total, through winters spent fabricating new brake shoes and summers threading fresh cable through 100-year-old sheaves. Every milestone was shared with a growing network of supporters, welders, machinists, local business owners, and families who donated lunch or spare parts. Some days, the workshop felt more like a community center than a machine shop, with stories traded over coffee about fathers and grandfathers who ran cable shovels in the pits. When the engine finally roared to life, the sound echoed across the yard, a low, steady rumble that connected past and present. Volunteers, some of whom had never seen a cable excavator in motion, watched as the restored machine lifted its bucket for the first time in half a century. School groups and museum visitors now gather around the 50B, running their hands over the smooth steel and learning about the daily rituals and skills that kept these giants alive. The machine stands as a living record, its scars and repairs a testament to the hands that built and rebuilt it. Preservation groups across the country have taken up the call, forming alliances to save the last survivors of the cable era. Museums coordinate with restoration crews, sharing technical drawings and sourcing rare parts. Fundraisers and public appeals help cover the costs of transport, casting, and storage. Each rescued excavator is more than a display. It is a reminder that durability is not just a matter of engineering, but of stewardship. Every hour spent restoring a cable excavator is an hour invested in keeping the memory and the lessons of the mechanical age alive. The machines endure because people care enough to fight for them, ensuring that future generations can witness the power, the craft, and the resilience that defined the cable era. Today, most machines are built to be replaced, not resurrected. As modern excavators struggle to reach even a fraction of their predecessors' lifespan, the cable era stands as proof that durability is not a relic, it is a choice. In an age defined by disposability, the real question is whether we still value what it takes to build for generations. Let us know your thoughts in the comments below.